Hi guys, so this is part 2 of a talk by Marek talking about how to achieve topological quantum computing with the Kitaev chain. In the first video he talked mainly about the basics of the Kitaev chain and how you actually have Majoranas in the system and some of the basic braiding properties. And in today he's going to talk a little bit more about how you actually achieve those braiding operations so that you can perform various logical operations. So, enjoy!
So today I will introduce a series of quantum gates. We worked on the logical Z operation with arbitrary angles, arbitrary qubit rotation. We will compare those gates, then we will conclude and talk about some other ideas. Each of those regular fermion operators can be expressed using two Majorana operators. The rectangular boxes are the lattice sides, and dots are Majorana operators, potential Majorana modes. And when two dots are connected, that makes a fermion. The Kitaev chain Hamiltonian can be grouped into three kinds of terms. The on-site lattice terms parametrized by mu, electron hopping terms parametrized by T, and the BCS coupling terms parametrized by delta. Fermions are delocalized in between neighboring sites, and there is a special fermion which is highly delocalized between the furthermost sites, and that's the topological phase. And with two such Majorana qubits, or two chains, we have 4 edges and thus 6 possible braids. And if you do the algebra, you would check their eigenvalues and eigenstates, and you would find that they produce square root of z, square root of yx, yy, xx, and xy gates. So there are 6 possible gates to achieve by doing topological braids of only the edges. So what about different ways to develop quantum gates using topological braiding? One possibility is the double braid sequence. If you double braid every side consecutively, you would end up with eigenvalue that depends on the presence or absence of highly delocalized quasi-fermion, which is basically the Z gate.
Is it possible to understand why that's a Z gate just from this picture, or is it just algebra?
I don't think there is an intuitive way to see why this is Z gate.
Okay, so this is a single chain, and then
we braid every side.
Okay, so if you braid every side, so in the previous slide you had something else that said if you braid the
edges,
ends of the chain, then you get a square root of Z, right?
Yes.
And then so if it were the ends of the chain, then of course that would be a Z, right?
Yes.
A double braid of the ends of the chain.
Yes.
Be Z. But then this is not a braid of the ends of the chain, but actually of the
every side,
of the bulk regions.
Yes.
As well, right? So yeah, I also don't know.
But the advantage of that is you do not need to create an interaction that reaches the farmost modes. You can achieve it using only the internal interactions.
Yeah, I see.
So I will explain you a different kind of notation right now. What you saw previously was the braiding diagrams. Now I will show you the adiabatic transition diagrams. So here the circles are single sides. The lines between circles are couplings. Here you see the coupling strengths, so they're all minus T.
So that's the parameters of the Kitaev chain.
Yes, exactly. The blue region is the topological regime, and the red line here, that can be also here, is the on-site potential value. So it can be either low, either high. And when it's high, we assume it's above the threshold of 2T. So here I will explain you how to achieve the double braid sequence adiabatically by acting on Kitaev chain Hamiltonian parameters. The left picture is simpler to understand, so let's start with that. if we just side by side sequentially change the sign of electron hopping from negative to positive and back, that would adiabatically correspond to applying the double braid sequence everywhere. But the disadvantage of this approach is you need to be able to control every side of the chain. You need to be able to change this hopping sign everywhere through the entire chain. That's why there is this alternative picture here, which looks more complicated. The price to pay is you need double the length of the chain. So for the domain of length 4, you need 8 sides. So what you do is you have only one special region where T has a different sign, and you adiabatically decrease mu in front of the domain and adiabatically increase it behind the domain. The topological domain will follow adiabatically the ground state, so we'll move further through the region of the different sign T. From the domain perspective, it works same as the left picture. The sign gets reversed sequentially side by side, implementing the double braid sequence.
So basically, instead of moving this plus region through the chain, you just fix the plus region and you move the chain through.
That's exactly
through
it.
that. Yeah,
exactly. So the advantage of that is it is achieved using only local braids, only local interactions within the chain. And the overall size of the domain is always the same, which implies that the gap between the logical space and error space should also remain intact, giving the full topological protection. The disadvantage is it gives us only a Clifford gate because Z is fixed to angle pi. We cannot rotate by arbitrary angle.
So you said like if you have a non-local fermion, then no matter how you braid, you can always be sure it's one of the ground state of the same Hamiltonian, but just with different parameters.
Yes.
But how do you know that?
Because you can apply universality of adiabatic quantum computation, which connects unitary formalism with adiabatic formalism. So if you just act unitaries on the Hamiltonian, you can find what would be the Hamiltonian of the ground state after applying this unitary.
Okay.
So we use this to just demonstrate which braid how affects which parameters of the Kitaev chain.
So is it easily sayable? Like if I do a series of braiding, each braiding is kind of like maybe pretty easy, like just one by one. But then how can you is it hard to get the parent Hamiltonian?
This is to implement particular braid, you mean?
Yes.
So it's not easy because how those braids affect Hamiltonian or vice versa, which changes of Hamiltonian apply which braids, that's very counterintuitive. For example, doing this sequence of braids is easy because that's just raising mu, side by side. But for example, changing doing this, the double braid, like that took us quite a while to find out what does it do actually. Like changing, hopping and back, like that was kind of strange. So this is not very intuitive. It's not like there's a simple rule. And also not all of those parameters are easy to control experimentally. Like mu is easy to control.
But what, on-site potential?
On-site potential. But T and delta, not so easy anymore. How to rotate this domain by any angle we want. So as it turns out, you can act on qubit, you can rotate a qubit without applying rotation directly to this qubit, but instead acting on a qubit that is entangled with it. And that's what is going to be applied here. So on this simplified diagram, this is the what we call coupler qubit, and this is the logical qubit. So if we apply this sequence of operations with control Z, it will be equivalent to just apply Z by angle phi here. Even though there was no operation that depends on angle here. Such operation was only applied to the coupler spin. And this approach is going to be translated to the adiabatic protocols we described earlier as follows. If, as you remember, applying the double braid sequence required having different sign of the hopping term in the middle, we moved the domain through the special region where the hopping term was different. So what if an extra sigma z is coupled to one of the couplings, and then it will pull out either +1, either -1, depending on the state of a corresponding qubit. That's what is often referred to as free spin coupling. And this allows us to implement the controlled Z gate in the adiabatic protocols on the Kitaev chain. Apart from that, everything is the same as on the previous picture. So if we move the domain through this special region, the double braid sequence gets applied only if the coupler qubit is 1. If coupler qubit is 0, the domain moves as if never happens because the sign of T is the same. And this allows us to translate this protocol into adiabatic sequence. So we do square root of x on the coupler like this. We move it through the chain, which is the first control Z. We rotate the coupler, we move back, which is another control Z, and we complete the entire protocol. And we end up having this topological domain here being rotated by angle that the coupler has been rotated in the middle on the step 5.
So the coupler is part of the Kitaev chain, or is it totally sort of separate to it?
The coupler has to be separate from the Kitaev chain, because if the coupler was inside of the Kitaev chain, that would correspond, the coupler is just sigma z. That would correspond to having an unpaired Majorana mode inside of the chain. So that's actually the disadvantage of this protocol, and that's one of the disadvantages, which is it's very difficult to implement because this coupler cannot be something inside of the chain, because that would require having unpaired Majorana 0 mode. It has to be something outside that still provides this kind of interaction. Nevertheless, the advantages are that still relies only on the local braids. It allows you to do any angle rotation, so it is a non-Clifford gate. The overall, and the disadvantage is, even if the overall length of the domain doesn't shrink, in the middle of the protocol, the domain gets entangled with the coupler, so coupler can act as a source of error. So coupler has to be really high fidelity for this to work, and this is what we call partial topological protection. And as it turns out, this protocol scales really well to arbitrary number of qubits, because we can introduce one more logical qubit or even more of them, and by having more controlled Z operations, we can create an entangled gate in this way. The adiabatic system looks more or less similar, but the important difference is now we need to be able to break coupling within the chain, because we are not allowed to have more than one topological domain in the same chain. That would no longer be the ground state of Kitaev chain Hamiltonian. They would start to interact and you would have very poor fidelity. So this works as long as you figure out how to move them through the coupler so that they can all get entangled, but they are never physically in the same chain. So you have to remember when to break the coupling and where, so that they never interact. But they all get entangled with the same central coupler. It gets rotated and it implements the entangling gate operation. And here we do it using the phyllo queue, first in, last out. So we just move them one by one. They all get entangled, and then we move them back in the reverse order because they have to return on the same path as they entered.
Maybe you can just talk through the steps and then match it to the circuit diagram.
So we have our initial state with two topological domains, and the coupling is broken, so they don't interact. Here the coupling is connected, but there is no topological domain here. It is a trivial domain, so it's okay. We start by putting the coupler in the superposition state, which corresponds to square root of x here. We move the first domain to the farmost edge, like this. So that's the first control z. Then we change the coupling here, so that now this one is connected, this one is disconnected, and we move the other one. So they never interact because they were never in the same chain. That corresponds to the other square root of, the other control z. Then we rotate the coupler just like previous by the angle we wish to apply, and we reverse all the operations as we did them. And that implements this circuit on the left using the sequence of adiabatic steps on the right. So the advantage is it preserves partial topological protection of the single chain counterpart. It scales to any number of qubits. You can put as many, as long as you have the patience of moving them one by one, but there's no theoretical limit of how many of the order of this gate. It implements multi-qubit non-Clifford gate. The disadvantage is the breakable couplings, which require more control over how the chain behaves, but we still manage to not have all the couplings controllable, but only every m sides where m is the length of the domain.
So what I understand is mainly like you trying to like analyze different kind of braiding, and then see what this braiding gives a logical operation.
Yeah.
Okay.
I'm basically searching how to create particular logical operation using only local boards.
So this may come up like a very stupid question, but suppose we only do local, but the operations we do is like very large. Suppose the length of lattice is L, and each time we do a local one, like labeling one, but the time we do, but it says like the number of operations we're doing is like pretty large. Yeah. Then when we multiply, or in the end we multiply them together, it seems like they're non-local.
Yeah.
Does that happen?
So that's why you have those long sequences of steps, because you do lots of local operations to achieve some global effects. I guess what I meant by local was that I search for operations, for braiding operations that give logical results on the logical space corresponding to certain operation, but also corresponds to variations of parameters in the Kitaev chain. So Kitaev chain would not have some crazy non-local interaction in it to create some, very complicated braid. So
no matter how you braid, so the state is always a ground state Kitaev chain.
Yes.
So by local it means like, okay, the interaction, I guess the interaction parameters of the Kitaev chain is always local. But
yes.
But okay, yeah.
So you just adiabatically vary the coefficients of the Kitaev chain.
So this part, the connection from this braiding to the adiabatic like evolution part, it's like is adiabatic evolution is like a way to achieve the braiding unitary.
Yes. So this paper actually connects the unitary picture and adiabatic picture.
Okay.
We actually connect how those braids affect the Kitaev chain Hamiltonian and vice versa.
Okay.
Yeah. So we talked a lot about the Z rotations. What if you want to do arbitrary rotation? What if you want to do X or Y or whatever? So that is a bit more complicated. we introduced the conversion operator previously. So if you imagine that if you convert the state from the topological regime to normal regime and apply gate locally and then delocalize it again, you would technically apply arbitrary operation to your topological regime. You can see this on the braiding diagram on the right. Like we basically localize this highly delocalized quasi-fermion here to apply the gate locally, and then we delocalize it back. And adiabatic protocol follows from that, only that the domain does not move. It shrinks to the single side, so it becomes just a regular domain. Then the gate gets applied, and we extend it again. The advantage of that is any operation that you can apply locally, suddenly you can apply it to your topological regime. However, your topological domain gets practically destroyed because you have to shrink it to the size of 1. So you have no topological protection of any kind. Your gap between the error space and logical space becomes 0. So let's have a look at some results. These are simulations of few of the protocols you saw earlier. The left plots is the Z rotation by angle pi, and the right plots is the arbitrary rotation about X, also angle pi. Initial state here is a plus state. That's why expectation value of X is 1 on the left side. And initial state of the X rotation is 0, so expectation value of Z is also 1 on the left. When we apply the protocols, we see that this goes from 1 to -1 through the entire protocol. So plus becomes minus. So the state got rotated by pi. And same here. We also see that the protocol is more complicated. Different things happen in the middle. The state goes from 0 to 1. So it got rotated about X. Let's take a look at the energy fluctuations. For the Z rotation, the energy fluctuations are really small in the units of mu. That is because every time we shift the domain by one side. During the transition, so during one adiabatic sweep tau, the state is not exactly the ground state of the Hamiltonian. It is a bit off, and this is where this fluctuation comes. So there are 4 peaks here because it goes 4 times back and forth. But those are very small fluctuations compared to mu. However, here, with the arbitrary rotation, we have to shrink the domain to size 1. So we destroy 2 sides. So every time we do it, the changes of order of single mu. So this one is much more destructive to the state and to its fidelity. Speaking of fidelity, we did a little fidelity study on those gates. Here we have the multi-qubit Z gate, 2 qubits, arbitrary angle, single qubit Z, arbitrary angle, and rotation about X based on the arbitrary qubit rotation protocol. The colors of the plots are the angles, as the legend shows here. And we can see that the fidelity reaches 1 once the adiabatic sweep tau is sufficiently long. So to summarize our gates, we have a bunch of UZ gates. One is fully topologically protected, 2 others are partially topologically protected. We have 3 non-Clifford gates. Sadly, the arbitrary rotation has no topological protection at all, but we do have 1 multi-qubit entangling gate, which is also non-Clifford gate. And currently, what we are working on, is we are developing a new kind of arbitrary rotation Z gate, which is based on geometric phase, in which we can create a relative phase by globally acting on mu on-site potential parameter, and we only need fixed rotation angle on the on-site braid. We already have some preliminary results. As we can see, it works same for different lengths of the chain and tends towards pi/2, which is square root of z, which seems reasonable for a single qubit topological gate, just like the braid of the outer edges. But it can also achieve different angles, so it would be a non-Clifford gate as well, not only pi/2.
Yeah, so I don't know. This is kind of interesting in a way because like just the Kitaev chain is considered to be something that only can support Clifford gates, but somehow I think in this you don't go outside the topological region ever. Is that true?
That's true, because to go outside of the topological regime, you would need to increase mu to up to 2, because it's in the units of t.
Right.
So, yeah, you're right.
So I think that could be the most interesting thing about this thing, because it seems to escape this, Clifford restriction, but yet it's still always in the topological regime. And then, you do that by basically changing the type of model, right? So you actually change the model adiabatically throughout it. I don't know if that violates some kind of no-go theorems, but anyway.
Yeah.